Good afternoon, YouTubers. It's February 5th, day after the Super Bowl, NFL Day, and which was in Atlanta this year. I watched it. So here we're talking about Waterman polyhedra and how they have whole number tetravolumes, and I want to get to that. I want this to be under 5 minutes and keep myself just to that point. So what you see is the growing IVM, you could say, the CCP. It's easily presented if you just follow this rule. Start with the center ball, pack six around it in a plane, like in a hexagon, then three atop and three at the bottom. But the three atop don't line up with three on the bottom. There's a twist in those two triangles so that you can't look directly down from a sphere on the top and see a sphere at the bottom directly below you. And if you follow that rule and pack outwardly, then you'll just have a growing cuboctahedron of spheres and all the way to the center, right? So layer after layer, but they're dense packed spheres. They're all surrounded by 12 neighbors except on the edges. So this is what we kind of consider a home base. It's kind of the holodeck of synergetics. And you could say ordinary XYZ math has its own holodeck, which is the XYZ matrix. And this is, just a different matrix. It's a scaffolding. You don't have to imagine that it exists somewhere any more than XYZ exists. It's just a juxtaposed kind of a ghostly addressing scheme, and you can treat the IVM like that, a set of grid lines that basically fill space with a different pattern. And crystallographers and many professionals, I've already thought this way for a long time, not new news. So the Waterman polyhedron starts at the center of this. The simplest definition, before we shift to voids or whatever, is going to start with that center ball and then pick another ball out further in the periphery as follows, as shown, and then find every other ball that's either that same distance away, and you're going to find a bunch because of the symmetries of the cuboctahedron. There'll never just be one ball distance x from the center, right? There'll be its sort of correlates, other symmetries. But then you want to get also all the balls of a lesser distance that don't interrupt the overall convexity of the surface. So the rule is it has to stay ball shaped. It can't have dimples. It can't be a stellate. It can't have bumps. It has to be curved, always convex. But beyond that, the vertices all have to be at the centers of CCP spheres. And with those rules and how we started at the center with one CCP ball, you get a sequence of Waterman polyhedra based on the initial distance of the first origin to the corner. That's what we'll call sort of your prime vector in this case. Depending on its length, you get to the different Watermans. Just notch it up a bit and keep seeing what you get. Now, I worked with Steve early in his career. He had gone to the Fuller Institute, or probably mailed his stuff to the Fuller Institute. And when I went through there one time, I saw what he had sent them. And later I wrote to him and said, "Gee, that's pretty interesting." And I think I have that letter still on file under my collaborations at Wiki Educator. So let's just go there real quick. Wiki Educator is a whole other website where I have my digital math curriculum and where I do some autobiographical stuff and where I have a record of some of my collaborations. I don't update this a lot, so recent collaborations may not be here, but the Steve Waterman collaboration goes back quite a ways. And if I click on I worked with Steve Waterman, I get to an old copy of my original letter to him, July 7th, 1993, and I'm putting him in touch with David Koski at the same time, and CC to Bonnie Goldstein, who was archivist at that point for the Buckminster Fuller Institute. So I'm asking to follow up with Steve Waterman on these on these Waterman polyhedra, and as he documents in his website, I was one of his early collaborators. If I click his link to my website, these are some early POV ray tracings I did. POV ray still to this day is open source, free download. It's not um, copyleft with it's a CompuServe heritage, but it is open source and free software. It just doesn't have the GPL. It's a different. It came from a different world, but a lot of people had that idea of how do we copyleft, how do we keep things public space, and then we can put our heart and soul into it, knowing that humanity will inherit it, not just a few spoiled kids or something, right? Keep it open, keep it free. I like that concept, that philosophy. And so does academia, really. So it makes sense that all this geometry would come together in an open space. Free ad for my own Oregon Curriculum Network. I've been sponsoring this for a long time to bring a lot of these resources to the public, including in the form of Python projects, if that's of interest. And you'll get more of that if you just watch more of my YouTubes. I wanted to keep this one pretty much limited to the Watermans, but on the way out, I want to mention they always have unit volume, they always have whole number Tetravolume, these Watermans. And I don't have the proof of that. That was a Bob Gray project a while back to prove it. I could generate random IVM tetrahedra, though, as kind of intimated by this animated GIF here on the screen, where you just pick 4 IVM spheres at random and connect them. That way you get a tetrahedron, unless they're coplanar, right? And then measure the volume in tetravolumes. Your unit is just 4 of those spheres packed tightly together. That's 1. And now what is the volume of these random things? Of course, they're all different. But they're not all different. But you get any whole number turns out, or is it any whole number? I take that back. I don't know that. I'm thinking probably not. But all the volumes are whole numbers. Whether you can get every whole number, as I think about it more, I think you probably can now that I'm thinking about it, because I think you can always increment by 1 somehow. Just shift the vertex. Yeah. Okay, interesting. So, Waterman polyhedra, defined in his classic sense of CCP ball at the center and all corners CCP, all have whole number tetravolume. That's a very fun and interesting entry point into the whole octet truss, isotropic vector matrix, all that. If you want to get into that through the Watermans, good access point. I recommend it. Talk to you more later.